Hello, mathematical reasoning students. What I'm going to do is go over sample test 2. Let me just give you a little preface or caution to this, in that the first part of studying for test 2, well, not only doing all the recommended textbook exercises, but this longer test 2 review, okay, is where you can practice the ideas more than just the sample test. Then, if you want to come in and time yourself on the sample test, this would be what I recommend. But don't just study this, because it doesn't give enough of the different types of problems we see in modules 4, 5, and 6. It's just supplementary. Okay, wonderful. Number 1, for x, y integers, we consider this statement. If x times y squared plus 2 is odd, then x is odd and y is odd. We're not asked to prove this statement. We're asked to state the contrapositive. So let me label a few things. If I call this part P and this part Q, my statement is P implies Q. And the contrapositive is not Q implies not P. This is what we want to write. But you notice that Q has an and. When we negate an and, this will become an or. Let's write this now. The contrapositive is if x is even or y is even, then this product, x times y squared plus 2, is even. One thing we can use in this course is that every integer is either even or odd, but not both, so that if you negate this part, x is odd, you get x is even, for example. Okay, that's all there is to this number 1. Now we move to number 2, which is strong induction. You notice the statement, we have a recursively defined function here, and the definition is given here. We are told a1 is 2, a2 is 9, and for n bigger than or equal to 3, we define an this way. What we want to prove is not a closed formula for an. What we want to prove is an inequality, that an is always less than or equal to 3 to the n. In a proof by strong induction, or even normal induction for that matter, we have 2 parts. We have a basis step, and then we also have an inductive step. Now, typically, as you know, when I'm doing strong induction, I will start with the inductive step to figure out how many cases I need to check in my basis step. So just in our thought process, let's start here, and then I can go back and make sure I check the right number of cases for my basis step. So the inductive step will begin something like this. Assume we have some integer with k bigger than or equal to, and I will fill in this part in just a moment. For 1 less than or equal to n, less than or equal to k, well, this holds. An is less than or equal to 3 to the n. We want to show for the very next one, namely that a k plus 1 is less than or equal to 3 to the k plus 1. So we have, now we are going to need to use this highlighted definition, recursive definition. So we have ak plus 1 equals, well, it's 2ak plus 3ak minus 1. Okay, this is our recursive definition. Now, here's where I'm going to use the inductive hypothesis. And I'm going to use it twice. So this is less than or equal to, first of all, ak is less than or equal to 3 to the k. So this would be 2 times 3 to the k, and then plus, okay. Now use the inductive hypothesis a second time. ak minus 1 is less than or equal to 3 to the k minus 1. Okay, so this is where, just as I was saying, we have used the inductive hypothesis, and I used it twice. Now, we know exactly now how many cases we will have to check in our basis step, because you see, I used the inductive hypothesis stepping back 2 times. I will need 2 cases in my basis step. But before I go back and do that, I'll just finish my argument here. This is 2 times 3 to the k plus 3 to the k. And then I can factor out a 3 to the k. And I have 2 plus 1. And finally, 3 times 3 to the k is 3 to the k plus 1. And so we have shown, if you follow this, we have equals and less than or equals all the way. We have shown a k plus 1 is less than or equal to 3 to the k plus 1. And this is exactly what we wanted to show in our inductive step. So I will put the box, even though I'm not fully finished with this proof. Okay, now, just like I said, you see, we stepped back 1 time, stepped back 2 times with our inductive hypothesis. And so this means we must check 2 cases in our basis step. And we are trying to prove for all natural numbers, the first 2 natural numbers are 1 and 2. So A1 is given, it's 2. This is certainly less than or equal to 3 to the 1, no problem. Okay, and the other one, we need A2. This is given, it is 9, and this is also less than or equal to 3 squared. No problem. And this is what we need in our basis step. And now one more thing to finish this proof is the first sentence. We assume k is an n with k bigger than or equal to the highest one that we verified. So I'm going to put a 2 here. And now everything will read perfectly. In our basis step, we proved this holds for n equals 1, n equals 2, and then we assume k is an n, k bigger than or equal to the highest one we verified, and for every natural number up to k, this holds. And then we must show for one more. This is how the strong induction proof goes. This was strong induction number 2. Number 3. We have an if and only if proof, and it involves sets. So this is set theoretic proof. And we are told each direction may be easier either by contradiction or contrapositive. Oh, so this is a fantastic proof to work through. We have a lot of things going on, but fundamentally, if you look at this, we are trying to prove P if and only if Q, right? Now, this has 2 directions. First of all, I have a forward direction to prove P implies Q, and then I have the other direction to prove Q implies P. So let me just state what I'm proving each way. So we want to prove if A is a subset of B, then A minus B is the empty set. Okay, and we will do this by contradiction. By contradiction. In a proof by contradiction, we assume this part is true. We assume this part is false. Both of those. So let's assume A is a subset of B and that A minus B is not equal to the empty set. And then we want to work until we get something that's always false, our contradiction. Here, what am I going to work with? Well, this gives me something to work with. A minus B is not empty. So as A minus B is not equal to the empty set, there exists an X in A minus B. Now let's translate what this means. Then this means definition is that X is in A and X is not in B. Well, we have to use this assumption, which we haven't used yet, that A is a subset of B. As A is a subset of B and X is an element of A, we see X is an element of B. And now you see our contradiction. Well, we have X is not in B and X is in B. That's always false. So this contradicts that X is not an element of B. So this is the end of this direction. Now let's do the other direction, which is we want to prove Q implies P. So let's prove if A minus B equals the empty set, then A is a subset of B. And then again, we have this hint, which is it might be easier to either work contradiction or contrapositive. I think in this direction, I'm going to work contrapositive. So let me write this by contrapositive. Let's assume that A is not a subset of B, and let's show that A minus B is not equal to the empty set. Okay, this would be contrapositive. Well, what does this mean? A is not a subset of B. Okay, it is a not. It means that this is not true, right? This part here is A is a subset of B. Now, when is an implication false? It would say this would be true and this would be false, right? And so this is precisely the meaning of A is not a subset of B. Namely, there is an X in A such that X is not in B. So there exists X in A with X not in B. And if I want to make myself slightly more clear, I will just add above. So as A is not a subset of B, this is what I was just verbally saying, but it's nice to have it in a sentence. There exists an X in A with X not in B. Okay. Now we just translate that one step more. We see that X, well, it's in A and it's not in B. In particular, this means X is in A minus B. Hence, A minus B is not equal to the empty set. And this is what I was trying to prove in this direction. And now my entire if and only if proof is complete. Okay, this was a fun one. Number 4, this is going to be a direct proof. The statement says if A divides X and A divides Y, then A squared divides X times Y. And this is for A, X, Y integers. Okay, let's assume A, X, Y are integers with A divides X and A divides Y. Let us show that A squared divides this product XY. Now, in this proof, we absolutely must use definitions. And this proof is about divides. Similarly, if we had a proof about even and odd, we must use the definitions of even and odd. This is quite important in a proof. So as A divides X and A divides Y, well, we're going to have two integers here. There exists, say, n, m integers with, we will have A n equals X and AM equals Y. This one because A divides X, this one because A divides Y. Now I'm trying to say something about X times Y. And so I can just multiply. We have X times Y, this is AN times AM, which is A squared times NM. This is looking wonderful. As n times m is an integer, we see that A squared divides this product. And this is exactly what we were wanting to show here. That this is the end. This is the end of our proof. Number 4. Number 5. For X not equal to 0, we consider the statement. If X is irrational, then 1 over x is irrational. And before we actually prove this statement, we are asked that if we're using contrapositive, what do we assume? If we are using contradiction, what do we assume? And then part C, we will actually prove the statement. Okay, well, in both of these, we are working under the assumption that x is not equal to 0. That does not change in any of this. But in a contrapositive, we assume not this one. So if this is P and this is Q, maybe I should add this. Say this is P and say this is Q. In a proof by contrapositive, you assume not Q and show not P. So we assume not Q here, which is that 1 over x is a rational number. And I can write it like this with symbols. Now, in a proof by contradiction, we assume P and not Q here. And so what this means is we have P, that x is not an element of the rational numbers, and 1 over x is an element of the rational numbers. This would be our assumption here. Okay, now let's actually prove this. Me personally, I'm just going to use contrapositive, and so I will mention that when I start my proof. By contrapositive, we assume x is not equal to 0 with 1 over x, an element of the rational numbers. We need to show, in fact, x is an element of the rational numbers. And we need to use definitions, okay? Well, definition of rational number, there exists, say, n, m integers with m not equal to 0 and 1 over x equals n over m. This is the definition of a rational number. Let me just make an observation before I work with x itself, and that is, note that 1 over x is not equal to 0. And this gives us that the numerator n is not equal to 0. Now, I want to say that x itself is a rational number, and all I have to do is take 1 over this and 1 over this. So I take 1 over each side of this equality, and I get that x equals m over n with m, n integers, and n not equal to 0. And this means that x itself is rational. And this is the end of the proof. I have stated this is what I wanted to show, and I have shown it. This is a proof by contrapositive. Now, our very last one, number 6, is a counterexample. We want to disprove a statement. When we do this, we give a specific example and then justify. Okay, so this statement says for A, B, C sets, if A intersects C equals B intersects C, then A equals B. And it's false. Okay, this is what we will prove it's false with a counterexample. And so let me just let A be the set, say 1, 2, and B be the set, say 1, 3, and C be the set 1, like this. Okay, I try to make the examples not too complicated when I'm coming up with a counterexample. Now, this is my counterexample, but not yet have I justified. That's what's coming right now. So we notice that A intersects C is the same thing as B intersects C, which is just this set, which contains the element 1. However, clearly, because I have written out all the elements of the sets, we have A is not equal to B. And so you see this, I have justified as true. This, I have justified as false. And so the implication is definitely false. And so we have a counterexample. This is the end of number 6. This is the end of sample test 2. Good luck on the test, everyone.